Okay, so what I'm going to talk about is looking at some of the applications of what you can use this. So starting from the simple stuff we've seen is that the two concepts I have is I need to get the time to my device, and then I have to do something interesting with that time. So as Peter's nicely shown and as Paul sort of talked about, we've seen how we can get the time to the device. So we can get the time to the device, say, within plus or minus 1 microsecond of accuracy. Now I want to use the time and do something fun and cool with it. So Peter had much nicer slides. We'll skip that. As sort of Paul was talking about, one application here is generating our video and audio references, but there's a lot more interesting applications we can do. So a few of the ones I'll touch on, looking at some time of day stuff, not so interesting. Our Genlock one, which is important, not as exciting. Then we'll get into some of our audio over IP, our video over IP, and the new TRO3, and see how we can use that. And we can sort of think about what are other applications we could do in the future. So you can sort of think of this as it's a toolbox which is now enabling a whole bunch of new applications and uses of this. Okay, so time of day, basically every device in our network now knows what time it is down to a microsecond accuracy. So we can use this if I'm doing router control. I can do deterministic switching, or my automation system can use this, or my billing system. So not overly exciting, but just a few simple uses of knowing what time it is. So looking at our time to phase conversion, so this is our Genlock. So as sort of Paul touched on, so the key concepts for being able to implement the Genlock, I need to have an epoch, I need to define the phase at the epoch, and then I need some equations to how to convert time from the epoch to my different signal phases. So I think you've probably seen this diagram before, but just a way of visualizing that, where we have at some point, the Big Bang, the epoch, I have all these different wheels are all lined up. The diameter of the wheels represent the different, say, frame rates or different rates. So NTSC is one wheel and PAL is a different wheel. As we move forward, they spin at different rates, and you get at different levels. Key thing is that it allows us to do this all deterministically. So in the standard, there's a whole bunch of equations which basically say I have a time and I want to calculate in Paul's diagram that comparator. You had to tell it what time does the next vertical occur. Well, that's the equation you use. It's in the standard. You just have to enter it. So it's reasonably straightforward. So we've sort of worked out all the math to figure out the phase of all the verticals, all the audios, all the signals of interest. And then if you're doing time code, because of how jam sync works and different people will jam at different times, it can all be done. The math is just a little bit more messy. Okay, so that's one application of how we can use this time. So we can distribute time to all our devices, and we can then use these equations to basically implement Genlock. So important, but kind of easy. We can also now use it in some of the new audio and video standards that go over IP. So we'll just take a quick review of those standards just so you understand them. So we have SMPTE 2022, and what it's doing is it's just basically taking our SDI video, it's putting it into packets, so it's making sort of RTP packets and putting them over the network. So it's a reasonably straightforward, take our stuff, put it over the network. This is, well, it's one way where we started. Now, if you want to do, say, applications like breakaway audio. So with 2022, all the audio and the video and the auxiliary space is all stuck together in the same stream. So you can't route it separately. You can't really process it well separately. So we can then use something like AES67. AES67 is a standard for taking audio and putting it over IP. So it takes your audio samples, puts them into separate RTP streams, and then you can route those separately. So you can do an audio breakaway, so you can switch in a different audio language or whatever you want to do with your audio. TRO4 is basically when I send my audio and video separately, somehow I want to make sure to put them all back together such that I don't have lip sync issues and I can reassemble them. So we'll sort of get into that. So that's what the TRO4 deals with. And then sort of a new standard that's coming out is something called TRO3. And it's basically looking at the idea, in 2022, I put all my audio, my video, and my auxiliary space together. well, that's not as friendly as I might want in the future. So why don't I have one RTP stream for my video essence? Let's have a separate RTP stream for my audio essence or streams. And let's have another stream for my auxiliary space. So I'm taking my video and breaking it into separate streams so that I can process it separately, I can route them separately. Yeah, and so in the case of TRO3, we use another standard for the video, which is called RFC 4175. For the audio, we use AES67, and there's a new standard, an IETF one, that's for the auxiliary space. Okay, so in the AES67 application, I have conceivably different microphones, different sources. I want to send those across my network, and I want to be able to reassemble them all together. So I want to have all my audio line up together nicely at my receiver. So how am I going to do this? How am I going to use my PTP, my 2059, to allow me to implement that application? Well, what I'm going to do in the transmitter is I'm going to, in the RTP packet, there's a timestamp, and I'm going to derive that timestamp using my PTP 1588 time. So using that, I'm going to put timestamps into all my audio samples. And they're going to be at 48 kilohertz ticks, because that's a nice frequency for audio. Then in my receiver, I'm going to basically, by using the current time at that device and these timestamps, I'm going to be able to line things back up. And so looking at a picture from the AES67 standard, when the audio goes into my transmitter, I sort of mark the time. That's the time I'm going to put into the timestamp. It then goes across a network which has some amount of latency. And then on the receiver, I have the same PTP time. So both my transmitter and receiver both have access to that same PTP time. I then dial up, say I want the delay from the transmitter to the receiver to be 10 milliseconds. And then I just basically make sure I play out the packet that was 10 milliseconds ago. And then it doesn't matter from what source they're coming from, because all the transmitters are all locked to the same source of PTP time, the 2059 time. So because all the transmitters are locked together, the receiver can ensure that it doesn't matter what the network delay is. One path could have been 1 millisecond, another path was 5 milliseconds, another path was 8 milliseconds. It's going to be able to reassemble everything together, so there's no audio-to-audio delay. So that's sort of one application we have for our the 2059 stuff. So in TRO4, we're now having the audio and the video separate. So we have the same problem. We want to ensure audio-video lip sync, or that there's no lip sync. So we're going to use a very similar idea. So in 2022, there's a timestamp, but the timestamp is random and arbitrary. What TRO4 does is it puts a restriction saying, no, you can't just have a random arbitrary timestamp. That timestamp also has to be locked to the PTP time, much like we do in AES67. So then using sort of the similar technique, in the audio, I basically say I want to, from my transmitter to my receiver, I want 10 milliseconds of delay. I play out the audio timestamps that were created 10 milliseconds ago. Same thing for video. I timestamp the video, I play out the video that's delayed by 10 milliseconds, and because they're both delayed by 10 milliseconds, I now can guarantee that the audio and the video stay aligned. So now I can have multiple transmitters, I can have different paths, and I can maintain audio-video alignment. Now when it comes to doing the implementation, there's a few little annoyances. So the RTP timestamp for audio is in 48 kilohertz ticks, and then it wraps the 32-bit number that rolls over. The audio is in 27 megahertz ticks, and it again rolls over at 32 bits. And so you can't just line them up. So when we see logically, you say, oh yeah, we just line up the timestamps. When it comes to the implementation, it's a little bit more messy. I mean, logically, that's what you're doing. Just from an implementation point of view, it's a little more subtle and tricky. Okay, so using TRO4, I can now have separate audio flows with video, and I can line them up and guarantee no lip sync through my facility. So another application of having all the devices with the same time. Okay, so I'll call it TRO3. That is now becoming a SMPTE standard, and so the standard is going to be called 2110. So in future meetings and well, you may not see it at NEB yet because it's a relatively new name. So where you hear TR03 moving forward, you're going to start to hear it called 2110. And so, again, what it's doing is it's got a separate flow for the audio, separate flow for the video, separate flow for the metadata. And the video flow is a bit smaller than 2022 because you've removed all the extra stuff. Logically, though, it's the same problem that TR04 did. We just also now have auxiliary space to also line up. So again, using that same technique of when it goes into when it's received in the transmitter, we're marking the timestamp. On our playout, we just have, because the devices are locked together, we just have to decide how long we want our playout delay to be, line up all the samples. So another way we can just use this timestamp. So we just sort of looked at through a system here as so you've got you're recording this person pulling out their hair. Okay, because they're getting ready for NEB or something, and they're like stressed out because their product isn't working. So as the signal basically goes through different processing chain or through different paths, different networks, possibly different processing blocks, it incurs delay. But by using these timestamps and by having all the devices locked together in the network, we're able to remove that so that when you get to the uplink encoder there, it can realign the audio and the video. So just looking at where we're at in the industry in terms of all the equipment. So in terms of the core switches that you would be purchasing, many of the manufacturers are adding 1588 to more families. So when you go to any of the major switch manufacturers and you go through their catalog, not every one of their switch today support 1588 or 2059. But more and more of their models are now adding that capabilities to that. Most of the switches today will support just say the 1588 default profile. The 2059 profile is being added to those switches. So in the very near future, you'll see various of the switch manufacturers sort of making announcements of them adding that capability. So they're all, not all, but several of them are actively working on this, and they're getting close on that. For the Grandmasters, there's sort of two different things you're seeing. There's Grandmasters that are basically companies that made video reference generators are now adding the 2059 support for them. So there's several on the market, either are on the market today or will be announced very, very shortly. And we're also seeing where we have regular just 1588 Grandmasters coming more from the, say, the telco space or other markets are now adding things like the 2059 profile. So there are, from two different directions, we're seeing Grandmasters that are available today or will be announced very shortly. Slave devices, AES67 has been using it for a long time. Those devices are available. Also, various video devices are either on the market today or just being announced. So when you go to NAB, you'll see probably a fair number of products that are being announced supporting 2059-1 and -2. So the products are definitely there. I mean, there may not be as many, but they're definitely becoming sort of real and available that you could purchase today or in the very, very near future. So in summary, there's a lot of different applications. So there's the basic Genlock application, but we can use it for other audio and video alignment. And the 2059 and the 1588 is almost like just a tool set. By having all our devices having the same time, it enables different applications. And if you guys maybe think of different things, with that toolbox, you can sort of probably come up with new and exciting ways to do stuff. So it may solve other problems in the future. And with that, I will pass it over to Paul to talk about some of the interoperability testing that's been going on recently.
All right, so to wrap up the evening, just so you don't think this stuff is all just in our imaginations, because SMPTE is often accused of, I'm sure you've heard me say, the society of many people talking endlessly and nothing ever comes out except talk. Superannuated managers thinking they're engineers is the other one. So this is a test report done by Jack Douglas, one of our participants in 2059 and who's chairing the interoperability testing. And he prepared this report for the VSF, and he was kind enough to give it to me to share with you. And it's a summary of what we've done so far for our interoperability testing. We had our first Plug Fest. So in the context of PTP, a Plug Fest means that vendors who make masters or switches or slave devices could come. And they had to sign up. There's a memorandum of understanding for confidentiality because you have a bunch of vendors in the room experimenting in their sandboxes, and the last thing you want is the ability for one manufacturer to go, oh, I see Lee's having some trouble there, or a resistor burned on him a little while ago, and you mail that back to the office, the next thing you know, his company stock's going down, your company. So there's a lot of confidentiality around it. It was done at Fox, a Network Engineering and Operations Center in Woodlands, Texas, y'all, in November. And the participants were, as you see there, Meinberg, who is a grandmaster manufacturer who is adding 2059 to their product, Tech, Sony, IRT, which is the German consortium of broadcasters engineering group, Fox DVB Link, that's interesting. Imagine Oregano. Oregano is another PTP company. They strictly make PTP, and they're very, very strong PTP experts. PacketStorm, Jack's company, who makes test equipment. Deus, who was doing some Xilinx FPGA development around PTP. Evertz and Cobalt Digital. There's some. Hey, Jack! How you doing, Jack? Use the chat box and send us a message. So here's some photos from the Interop. Jack, can Jack see the photos? Yeah? Okay. So there's the photos from the Interop. And Jack, where's Jack?
He's on the camera.
He's in none of the photos. You see the trouble? No, there's Jack in the back. No, that's Tom. Well, we don't know where Jack is. We don't actually, yeah, sure, Jack was taking the pictures. Anyway, this is just the room and proof that there was activity going on. This is the coolest scope photograph in the middle, and I'll stay by the microphone and I won't walk over there because you want to hear me on air. But that actually shows the alignment of a number of slaves producing PPS signals, all happily and just about coincident. So that was very, very cool. The sort of tests we're doing are on this page. I won't go over them all. But they're not only on the PTP side of the world, but a bunch of things such as 2059-1 output phasing for PAL and NTSC. We didn't do NTSC because it's kind of tough, because it's only every 1,001 alignments. But we did do PAL. And we discovered that, yes, indeed, the formula in 2059 all work, and indeed, multiple people could have gone and built their own things and bring them in and plug them in a scope, and the signals lined up, and like, we were just ecstatic. And then we also played with network impairment. So in addition to verifying this stuff works as expected and beginning to get a feel for how it really works, because it's only been theoretical to this point for most of us, we were actually able to pound on it a bit with some network impairments using Jack's test equipment that his company makes. And that allowed us to see where the stuff broke. And we didn't exercise it thoroughly enough, and you'll hear later there's more work to be done. We reported through a spreadsheet system. We had columns of vendors, and we had suites of tests, and these were bounding tests. We said, okay, well, we'll try message rates this low and this high, and you know, try to get a feel for it. We obviously could spend 10 years going through every possibility of combinations to try and figure out all the permutations of what works and doesn't. And what we really need to do is kind of converge on something. So this was what was used for reporting. And we made these conclusions, and this is very exciting to me. 2059-1 and 2 fundamentally work as intended, which is a great relief for some of us who've worked on it for a while. Only minor clarifications are required to the standard document, which was published 1 year ago. The performance goals for lock time and accuracy are achievable. So this surprised some of our PTP people who said, like Peter did, typically it's 2 minutes, and I understand that's true. But we had a number of implementations come, and you plug them in, and 2 or 3 seconds later, bang. Okay, well, it's doable. We're not sure exactly how, and it's not our business to constrain it, but we've seen people do it independently of each other, so we know it's doable. We're not sweating that anymore. We actually tested all of the areas we intended to test to various degrees of depth, depending upon the equipment that was brought and the capabilities of that different equipment. I mean, these are real early days. So we had prototype stuff. We had one company, as I mentioned, with a Xilinx development board evaluating code, right? So in future Interops, we're going to expand these areas of testing, especially the timecode math verification. And I'll take a side here just to basically say calculating the real time of day from PTP time in the context of 1,001, 1 over 1,001 frame rate timecode is a bitch. It's really difficult. And we actually did something in 2059 that was never done before. We actually formalized the daily jam time. So you now have to tell your master generator what time you do daily jam. Otherwise, if I turn on a generator in the middle of the day, excuse me, a slave, and I plug it in, it doesn't know when the jam happened. It cannot make timecode in the right sequence unless it knows when that jam occurred sometime in the middle of the night. So we've done some things to actually tighten up the world, but the timecode math is hideous. It is terrible, and we really have to spend some time there. We highlighted the EGs, as Peter noted, and poor Peter, you're talking about it being so important, and I leaned over to Lee and I said, I guess we better write them, because a number of us have them assigned to us to do the first draft of them. they're quite behind the curve. And they provide, both the background, but as well as just an overall broad understanding of what's going on and help people deal with the complexity here. We found some clarifications that need to be made. Communications mode was one that would benefit from some clarification. You have no idea what confusion is inside that little sentence. And overall, working together really helped, I think, improve everybody's products. It was beneficial for everybody who participated. We all learned about PTP at 2059 and discovered that, some of us are stumbling on our own bad coding and some of us are stumbling on the same thing other people are, and we were able to help work through some of those. So we have some feedback for the standard. There's a one-year review in every new SMPTE standard, and that's coming up for 2059. So we're going to clarify some language. We're going to clarify the length field. This is all kind of unimportant to people. I don't really think we need to see this stuff. Jack, it's off the screen. Jack, it's zoomed too tight. Jack's slides went off the screen. And we have some suggestions for the next time around. So we're going to specify some minimum I/O requirements to make sure participants bring enough of the output signals we need to be able to test. We're going to be able to measure lock error on all systems using external signals. This time we were kind of limited with 4-channel scope and things. We're going to do the multiple active master test where we have multiple masters on the network and one of them is, so I'm the strongest. And then we pull his plug so he's weak and we make sure everybody, switches correctly and cleanly and slaves don't freak out and wander to different times. We're going to break the profile test into both a functional and a performance test because the profile defines the performance of the PTP in terms of a bunch of parametrics, especially the message rates, but there's also functionality buried in the profile. So not only do we take information about PTP and shove it in that profile, we take information about the SMPTE side. Things like the frame rate, by the way. Did you know that the one thing missing from PTP is you cannot tell the slave if you're a 5994 or a 50 hertz plan? There is no mechanism. So this sort of stuff had to go into the profile. So receiving equipment say, oh yeah, I know I'm in Toronto. I know I need to make 5994, not 30 or 25 or whatever. We're going to test both 1- and 2-step modes. These are network operational modes. We're going to test the corner cases of the profiles. So will it lock up in time at the highest message rate, the lowest message rate, and so on. We'll test different network topologies. So we'll try a core and 2 cores and spine leaf and a bunch of things. And the topologies also will include switch types, unaware switches, boundary clocks, transparent clocks, and so on. SDVNs for that matter. IPv6 will probably be on the table for the next Interop, although that's a little bit down the road. Real-world network impairments. We're looking for statistics on this stuff and people who know about it, and we've got a couple of experts already, including Jack, on the team. And then we're going to do some kind of finicky stuff at the bottom here, just related to performance characterization. So, actually, middle of June, we're going to be back in Texas, eating barbecue. And it's a wonderful place, by the way. It's a fabulous area and not bad barbecue either. So there's going to be one there. There's going to be one in Germany, July, August, probably more like August. And the Europeans will be able to participate more readily in that, and we'll be able to demonstrate at that time perhaps to some of the European broadcasters, depending on the terms of where we're at with confidentiality. We may be able to put together a presentation for them, as we're able to do here in North America in October at the SMPTE conference in California. We're actually going to have a live demo of all this stuff running, various people's equipment, all playing happily together, and one big happy circle. And we're now working with AES, because it's been realized that the PTP profiles for 2059 and AES are very close. Retrospectively, we actually knew this, and we didn't do the right liaison at the right time. We really should have, but we're close enough, and we're now talking to them, and we're looking to find a way to merge them into a single profile that will work for all media and satisfy the requirements of both groups. So we're working on that with them. They've formed a task group to work on their side, and we're doing the same thing. And that's it. And thank you, Jack, for this slide set so we can talk about the Interop. And thank you all very much.